Welcome, I'm David Pommerenke. I'm professor at Graz University of Technology in the electronics lab. And in this video, you can learn today about IEC 61000-4-2 ESD testing. The testing is relatively simple, but we want to explain how to do the test that you get meaningful results. Let me explain. First thing, we have a typical ESD generator here. And on the top of the ESD generator, we have this little current capture unit. This unit is a very small magnetic field probe, and it's so small it doesn't influence the current at all. If you wanted to measure the current using a current clamp, then the current clamp would change the current. And this is very lightweight. It connects to a coax cable to a deconvolution unit because magnetic field sensors give the derivative, so we have to do some integration. We do a multi-level integration, and then we go to an oscilloscope, and the oscilloscope is right now set to 500 megahertz bandwidth, so we can observe the current. So let's take a look at the current. For example, I will just discharge here. This was an air discharge current, not very well defined, but we capture the current as it flow. The next thing we have is ESD protection in case you need it. The scopes are very sensitive, very easy to destroy, so we put ESD protection units in front of the scope, and since we do that, we have not lost a single channel. Otherwise, we have the same noise scan ESD generator here. Now, what else do we have here? This is an interesting unit. This arm contains a light. We don't need the light today, but a camera. And the camera can record exactly how we do the testing. For example, here we can show the back side. And let's say I attempt an ESD discharge to the connector here. There was no discharge, or I attempted here. There was no discharge. But sometimes there's a discharge and the unit may crash. So we record the current. We have exact recording of the exact current when it crashed. And we have a recording of the angle of the approach, etc., etc. So this arm is very flexible. We can bring it pretty much every position, so we can shine light and we can record every aspect of testing. So the data is meaningful because we show how it was discharged. We can record how the crash was, for example, and we capture the exact waveform of that specific discharge. This is the beauty of this test setup. So we have our ESD generator now. Now I'm changed to 8 kilovolt. I'm in air discharge mode. I'm going to do something which is not part of the test setup. So I'm going to discharge in air discharge mode against this computer. And we are observing the computer here. And we can observe the way I discharge using this camera. So I go to single trigger and I discharge. And now the monitor crashed, or the system crashed. And here we have the associated waveform from exactly that crash. So let's do this again. And in air discharge, we know the waveforms will vary a lot during the spark length. Let's do another discharge. Crashed again. Let's do another one. Okay, let's look at another discharge. We are ready again, 8 kV. And we see a very gentle waveform. We had a long spark, and the system did not crash. Let's do another one. Let's approach fast. And we see it crashed, it recovered in this case, and we have a very steep waveform here. So now we can correlate the way I approach, the speed, the angle, to the current and to the DUT response. And the whole thing can be recorded for a test report. Now let's go to another phenomenon, which is highly ugly. It's the secondary discharge. So you discharge to an object, the object charges up and there's a second spark. This can happen, for example, if there's a decorative metal on one device and that device discharges to ground. So a secondary discharge has very high current and it may be very close to the electronics. So we want to illustrate that. And we illustrate it simply by this object. The wrench is lying on the insulator, but a little bit I extend it to the metal. So when I discharge here in contact mode, there will be a secondary discharge. And we're going to record the currents here, and we're going to show you the effect. So we put this camera such that we can maybe see the spark. So first, we will just do standard contact mode, and we can observe the current here. So what do we see here is a standard pulse. I didn't discharge to a ground plane, I just discharged to the edge of the metal, but it repeats very well from pulse to pulse. So I do pulses. These are like about 2 pulses per second. They repeat very well. Now, let's discharge to the wrench. And now, when we discharge to the wrench, we see the initial pulse. This is the charge up of the wrench. But then a little bit delayed, the delay will depend on many parameters. We see a secondary breakdown. This is a secondary discharge, and it is very ugly. It's very unstable. It will move in time and sometimes occur, sometimes not. And the rise time may be much faster than the original rise time. I'll give you some more pulses. And every pulse is different, the delay is different. So here we see an initial pulse, a charge up of the wrench, and then after a delay, we see the discharge of to the ground. So this is secondary discharge. We can observe it. We capture the current, and we, of course, may be able to see the spark on this monitor. So let me summarize. To make this ESD testing more meaningful, we have to know what happened to the DUT when we discharge. And we know, especially in air discharge, every discharge may have a very different current due to the spark length. And so what we set up a system where we can capture the current of every ESD. We have like 500 megahertz bandwidth on the scope. And then we have the highly flexible camera and light, so we can record exactly how testing is done. Approach, speed, angle, if there's a spark, etc. And now one can say, if the unit crashed, we know exactly the current at which it happened.
You're the signal in my static home.